So this video is going to talk about how to use the time error tool to analyse a capture. This capture is one that Hong Yang did for us in Australia. Now the equipment getting checked wasn't claimed to be a high performance in terms of time error. In fact, it's actually got some interesting characteristics, and that's primarily why I've used it here, just because it really helps to show what you can do with the tool in terms of analysing. So what was happening here was it was a BC that was being tested, and Paragon was connected in the output and using its slave to terminate the flow coming out, and was also looking at the 1 PPS coming from that slave, and was stimulating the slave on the input side from the Paragon master. So we have a capture here that's exiting or egressing from the TC, and what we can do is send it to the time error measurement tool. Now when this first comes up, what you'll see is a fairly typical noise pattern. It really doesn't tell you very much what's going on. You can look here, there's a lot of interesting stats. It's got the min, minus, max. So you can see there's almost 1 microsecond of noise, probably roughly about 600-700 of kind of noise here, with the odd spike of about 300. And it's roughly, you know, in terms of just eyeballing, reasonably distributed around 0. But really, apart from that, you really can't see very much. And the problem is the noise in terms of the packet-to-packet noise. If you zoomed in very closely to this, you will see it's a very hairy pattern. Basically, there's a lot of noise on there. And of course, the slave's going to ignore all that information. And what they're talking about in the standards is always applying a 0.1 Hertz filter, which in some ways is, you can treat to a first approximation as a simple averaging. So if you go to constant time error and put the moving average here to 10 seconds and hit plot, what do you see? Well, suddenly you see something that's far more interesting. Suddenly you can see a clear pattern that's happening underneath, and that's the pattern that's basically going to affect the slave. If you look at the min, minus, max now, it's dropped from over a microsecond to just over 100 nanoseconds. So it's not too bad, other than the fact it is offset. As you can see, we can set limit lines here at 50. There's one at plus 50, which you can't see there, and minus 50, and it has failed. But it's got 100 nanoseconds of noise variation on the two-way constant time error. Now remember, the two-way is the most important measurement because that's utilizing both the forward and reverse. But if you look at this, you can see there's clearly wander noise, but every so often there's a step going on, which is interesting. So we can have a look at the one-way T1 and the one-way T4 to see whether we get any clues. So the T1 is effectively the error introduced in the sync message as it comes out. So if we look at that one, you will see that suddenly there's no longer that step, but there is a wander pattern going on there. And if you go to the T4 one and hit plot, then look, lo and behold, you see this step. In fact, you can see T4 normally is very predictable on the input, but every so often there's a step here of roughly about 80 or 90 nanoseconds, which I believe this was a 100 meg interface, and that's exactly what's happening as a buffer. 100 megs, or 1 byte at 100 megs is about 80 nanoseconds. And it looks like as the signals come in on the line clock and transferred to the internal clock on a FIFO, it keeps changing its fill state by plus or minus 1 byte. And you can see here clearly sometimes there's an extra byte delay, sometimes there's not, and it's causing this step. So I would suspect on the input that there's some buffer that's causing this. And in fact, if they were able to control the design so that this step didn't happen, or they were able to compensate for it, you could see the peak to peak would actually be very low, potentially down to 10 or 20 nanoseconds of noise. You may have also noticed that there's a fairly big offset here of 8, nearly 9 microseconds, but that's actually okay, because if you look at the T1 in the forward direction, there's also a big offset of minus 9, and in fact that's why when you did the two-way it came down to near 0. And every piece of equipment we've looked at so far tends to have that offset, and that's not a problem provided it's balanced. Remember, the most important measurement is the two-way, because that's the one effectively the slave uses downstream. We can also show the correction fields, the forward and reverse. Now in this capture, unfortunately, they weren't using the correction fields, but that's pretty interesting as well, because what we're seeing is that quite often people use the correction fields on the output of the slave to compensate. So they're measuring the delay and then they're putting the compensation in the correction field rather than adjusting the timestamp. And that's perfectly legal, and it's okay to do that. And you can see that it defaults to always include the correction field in the pattern. But sometimes it's worthwhile ticking that, to untick that, and then you'll see the calculation without it. Now, one other thing you need to do, as I mentioned at the beginning, is actually compare it to the 1 PPS output. So if I actually now call in the 1 PPS output here, it looks remarkably similar. If I actually just put the markers on here, roughly at, just very quickly here, put on the markers to calculate the peak to peak, you'll see it's roughly peak to peak 116, and here 121. That's pretty close. That's pretty damn close. So really what you're saying here is that all this noise is the phase noise in the clock recovery internally, because it matches the noise that's coming out of the 1 PPS. But as we've seen, there's actually there's also a packet effect happening on the output, which is coming from the delay request coming in, or the T4 timestamp, and you can see that very clearly. So this is a good example here of where you can actually show people how they can use this tool to actually solve the problem. First of all, characterize their equipment and then solve it. And as I said before, if you then look at the two-way, if you were able to take these steps out, the peak to peak would come down to probably around 20-25 nanoseconds. So there's two problems. One, you've got to figure out why this buffer keeps changing fill state and address that. And secondly, there is a bit of an offset in here. If this pattern was moved up to be centered closer around 0, in fact it would have passed the constant time error limit of 50 nanoseconds. And again, you can see here we show that on here. So really the tool is actually very powerful for doing this. We've done a lot of testing lately, thanks to people at Hongyang and Eric Craig doing lots of captures in the field, and it is very easy to use. Always put the averaging on. When you look at the raw data, you will find that quite often you don't see very much at all. It's pretty hard to see anything from it, but if you just go to the two-way, and even if you average over 1 second, it's effectively like a 1 Hertz filter on it, just to take that noise off, you can immediately start to see the underlying characteristics and the key characteristics that will be affecting the slave.